Video is just going to go over a little bit of the vocabulary you're going to want for this upcoming unit. So here we're going to take a look first at the zeros of the function, and the zeros is just another word for x-intercepts. So the x-intercepts of a function are where, or the zeros of a function are where f of x is equal to 0. So we're just looking at all of the places here along the x-axis. So we'll notice that there's an x-intercept here at -3, 0. There's another one here at the origin. There's one here at 4, 0, and there's a last one at 6, 0. So those can be identified from a graph, from looking at the graph, or by solving an equation to find out when the function is 0, when y is equal to 0. We also have maximum and minimums, and here we're going to refer to them as relative maximum and minimums. And relative maximums and minimums are for a given section of the graph. We have a relative maximum. You'll notice here we can't call it a absolute maximum because this graph's going to keep going up towards positive infinity. The y values will head towards positive infinity along as x goes to positive infinity or x goes to negative infinity. So really it's just a maximum for this part of the graph. That's why we call it a relative maximum. And then we also have relative minimums here. And the y-intercept is, of course, where that graph intersects the y-axis. So the y-intercept is where x is equal to 0, and here the y-intercept is 0, 0. Okay? So we're just going to talk a little bit more about multiplicity of zeros and symmetry from looking at these graphs here. So here I've got a graph that's in a factored form. You can notice it's got zeros at negative, I guess I should start in order, -5, right? It's got an intercept here at -5. Notice the difference in the signs. It's got an intercept at -2, and it's got an intercept at +2. This is a cubic function. You'll notice it comes up and then goes down. So it sort of 2 loops on it that identifies it as a cubic. And if we were to change this function, if we were to change one of these intercepts, for example this one, to x + 2, notice that the graph, so it was, right, +5. Notice what happens is it changes to +2. Notice we still have the general shape, but it's only adjacent. It's tangential to the x-axis here, and then crosses the x-axis here. So here, at this point, at -2, 0, we actually have 2 factors that would solve to be -2. So we would say that that has a multiplicity of 2. There's 2 factors that give us that same result. Okay. So that's the number of zeros that solve to give us here. So that's what we mean when we talk about the multiplicity of 0. And then symmetry, of course, is something that we're going to talk about. And symmetry is probably easiest to see when we look at a parabola. A parabola has an axis of symmetry, right? It's doing the same thing on both sides. And a quartic that looks a lot like a parabola, but just a little flatter, also has that axis of symmetry. So we can see that's just a little flatter there. Okay. And some graphs that we'll see will have very clear symmetry, and other graphs will not be as symmetrical, right? Won't have that axis of symmetry that we're rotating around. Okay. So those are the sort of general vocabulary terms that you want to know. You're also going to notice that there's a specific shape to different functions. So a constant function, right, where you have a function equal to a number, those are just all horizontal lines, like y equals something, like y equals 5, for example. Linear functions, first degree functions. Quadratics, raised to the second power. Cubics, right, has a maximum of sort of 2 lumps. Quartics have a maximum sort of 3 bumps, if you will. Quintic, 1, 2, 3, 4 bumps. So notice there's sort of one fewer number of curves, if you will, than the degree of the function. Now there don't need to be that many, but there could be up to 1 fewer. So if you have a function f of x is equal to x to the nth power, then the number of relative maximum or relative minimums that you have is equal to n minus 1. It's 1 less than the exponent. Okay, so again, 5th degree, 1, 2, 3, 4 relative minimums, maximum and minimums. Okay. And then we're going to talk about end behavior, and end behavior is just describing sort of where it's coming from and where is it going. So here we talk about as the function goes to positive infinity as x goes to negative infinity. So if we go towards the negative infinity, the y is going up forever. If we go to the right, towards positive infinity in the x direction, the y is also going up forever. If we change the leading coefficient to a negative leading coefficient, that just flips. So the f of x goes from negative infinity to negative infinity. In an odd degree function, the function goes from a negative infinity, right? The f of x goes from negative infinity over here up to the f of x going to positive infinity. Or if we flip it, it goes from positive infinity to negative infinity. So the end behavior is really just talking about sort of where those ends go off to. And looking back at our graph, we can see that for x squared, we end up, right, we're familiar with our parabola. For x to the 4th, we have sort of a flatter bottom. Or this could be extended to give us that curve. If we have an x to the 6th, we could fit now up to 5 lumps in there. But the end behavior will always be positive, f of x positive, f of x positive. Okay, same for x to the 8th power. Whereas those odd functions, I forgot our most common odd function here, our linear, or first one we learned. The odd functions the f of x goes from negative, the y goes from negative infinity to positive infinity if the leading coefficient is positive. If the leading coefficient is negative, then of course it comes from positive infinity and goes down to negative infinity. Okay, so that behavior is true for all of those odd functions. And here we could have, so for the green x to the 3rd power, right, we could have a maximum of 2 lumps. X to the 5th could have up to 4 lumps. 1, 2, 3, 4, and then I would have to go back up and away in that direction. So the number of maximums and minimums, the end behavior, and the zeros of a function can all tell us a lot about a function. All of these, right, they all go through the axis at the same point. They all go through at 0, 0. So these have multiplicities of, the multiplicity of these zeros is high. So for this purple one, for example, the multiplicity of 0 is 5, right? Every power of the x solves to 0. And so those words are going to help us when we're working to describe and define functions. So we'll be talking about that more in the next couple of days, but I hope that this video gives you a point of reference to return to to help formulate your questions.